Welcome to the second lecture in riparian function and management. The purpose of this course is to introduce students to the components of physical function in riparian areas and build understanding about how that condition can be influenced by management decisions. Successful completion of this course will be marked by the student's ability to evaluate riparian conditions, to identify potential for improved functional condition, to identify hindrances to riparian recovery, to envision recovered conditions, and to identify limitations to recovery capability. In our last meeting, we discussed the course organization, the details on reading material and required books, course structure, grading, and schedule, all which can be found in your syllabus. Also, you saw and heard descriptions of what is riparian, how despite its small size on the landscape, riparian areas have large influence over water quantity and quality. You also learned the components of functional condition and saw how physical function is responsible for producing much of the value that people appreciate about creeks and rivers. You saw many examples of functional versus dysfunctional, and we discussed water storage capacity, or the presence of a riparian sponge, as a common characteristic of the functional condition. The understanding and language of riparian is based on the interaction and interdependence of soil, water, and vegetation. These three components are dynamic and interactive. Imagine the riparian area working like a finely tuned machine where the soil, water, and vegetation are all the gears. You can start with introducing the terms relating to the water gear, but we will quickly begin to see that the soil and the vegetation, we will quickly begin to get into the soil and vegetation because they are integrally related. Hydrology is the knowledge and study of water. The hydrological cycle, or water cycle, describes how water evaporates from the surface of the earth, rises into the atmosphere, cools and condenses into rain, snow, or ice, and then falls again to the surface as precipitation. You will recall from third grade that there is no new water on this earth. In fact, we are using the same water that the dinosaurs drank, but that water has been recycled over and over again. Both soil and vegetation play large roles in the cycling of water. During the Dark Ages, people believed that water in rivers flowed magically from the center of the earth. An investigation into how springs rise and how rain forms was taken up with the publication of 1674 of De l'origine des fontaines by Pierre Perrault. In the book, he describes the big hydrology question of the day: where does the water in the Seine River come from? He theorized that to answer this question, one would need to measure water in the river as flows from its source to its confluence, and determine what portion of the precipitation that fell within the basin were contained. He found the river to contain about 1/6 of the precipitation that fell on the basin, and he surmised that the difference might be made up by evaporation and infiltration, or runoff. Others perfected his techniques and furthered his water balance theory. Precipitation in Texas is mostly rain, and more of it falls in the eastern part than the west. Annual rainfall averages across Texas range from 80 inches per year over the Neches River Basin to only 10 inches per year in the western edge of the Trans-Pecos region. As Perrault theorized, we now define a watershed as an area of land draining into a particular body of water, what he calls the spot where it joins together. This landscape collects and transforms precipitation into runoff or infiltration. We can either think of it in the landscape as a watershed or as a water catchment. We have all seen water catching and water shedding conditions on the landscape. In this particular picture, you might assume that you're going to have quite a bit of water catching in the grassy area seen there on the left, and oppositely on the right, where there's not much grass to catch the water, you might have a lot more water shedding or runoff. Factors influencing infiltration can include rainfall intensity and duration. Storms can be so intense that infiltration can be impaired by time. Soil types. Clays are less permeable than sands, for instance. Soil conditions, compaction or previous saturation. Factors like porosity and suction head contribute to hydraulic conductivity. Slope of the country where the rain is falling. And most importantly, the one factor we have most management influence over, vegetative cover. Many of us are accustomed to influencing infiltration on grazing lands, but this is relatively a new way of thinking in urban landscapes. Obviously, paved surfaces become impervious to infiltration, and in urbanizing watersheds, this can mean enormous increases in runoff and energy reaching streams. This diagram, presented by Harris County hydrologists at a recent conference, illustrates the impact of growing impervious cover. On flat coastal prairies, they expect 10% runoff from regular storm events. Each new house, rooftop, sidewalk, patio, and parking lot adds predictably to runoff, approaching the point where most of the precipitation during a regular storm will run off. The problem of impervious cover and dramatic increases in stormwater runoff from urbanization have manifested in reduced recharge of groundwater, in degradation of stream channels by excessive energy being delivered, in water quality problems and flooding, in spawning of all kinds of abatement schemes, the latest group of which are called LID, or Low Impact Development Guidelines. The term low-impact development refers to systems and practices that use or mimic natural processes that result in the infiltration, evapotranspiration, or use of stormwater in order to protect water quality and associated aquatic habitat. EPA currently uses the term green infrastructure to refer to the management of wet weather flows using these processes, and to refer to the patchwork of natural areas that provide habitat, flood protection, cleaner air, and cleaner water. It is difficult to discuss water cycle and water balance concepts without considering evaporation. Evaporation is the vaporization of water, and it is an endothermic process, meaning that heat is absorbed during the process. How much evaporation takes place, how fast, all depend on a number of conditions, including temperature, humidity or the amount of water vapor already in the air, wind, and surface area. Vegetative cover can shade and buffer or otherwise influence each of these factors. As with infiltration and runoff, the way we influence evaporation is through management of vegetative cover. With the water cycle and water budgets in mind, let's revisit the parallel question. Where does the water in a river come from? All stream flow originates as precipitation, which either ran off or infiltrated. A stream represents the path water is taking across a landscape. But the water flowing in the stream could have come from any variety of sources. Sources could include springs, like groundwater discharge or water stored in banks. It could come directly from rainfall runoff. It could come from a tributary river, or more often than not, these days, it could come from wastewater discharge. In Texas, water law and regulatory policy treat groundwater differently, and for the most part, separately from surface water. Surface water in its natural beds and banks is owned by the state and is apportioned through a permit system based on priority rights, popularly known as first in time, first in right. Certain expectations have historically existed for riparian landowners, even if they were last in time, to allow diversion of stream flow for livestock and for household uses. Groundwater at all depths, by contrast, is considered to be private property owned by the surface landowner. More than 100 years ago, the Texas Supreme Court adopted the rule of capture, which allows surface landowners to pump as much groundwater as they want from beneath their property, all with little regard to the effect on surface water. This system has been tempered over the years, but is basically still the rule. The water stored in the riparian sponge represents the interconnection between ground and surface waters. The old-timers called it bank storage and noted that its magnitude in some river basins quite exceeded the typical base flow. Not all stream locations have bank storage visible as riparian sponge. In some places, even perennial streams have lost their sponge. They have no water in the bank, so to speak, causing them to run dry when their surface flows and other groundwater sources become interrupted. Stream channels are where hydrology meets geology. Water meets soil and has spawned a new area of scientific study that we call Fluvial Geomorphology. Fluvial Geomorphology describes shapes and actions within river channels. Fluvial geomorphology includes consideration of channel dimensions, pattern, and profile, augmented by consideration of channel roughness. Channel roughness is described by Manning's equation, and it's important because roughness dissipates stream energy. Manning's is the genie of fluvial geomorphology, but it mostly considers cement versus grass, and typically it ignores the variety of roughness and stability provided by a large variety of specialized riparian vegetation. This chart of Manning's roughness values compares a grass-lined conveyance with a concrete-lined one. The grass mentioned is probably common Bermuda, which, according to the chart, offers a roughness of about 0.04. This is compared to the concrete lining, which is about a third as rough, with a value of 0.015. Some tall riparian grasses would likely offer a roughness greater than Bermuda, but less than a tangle of trees and overgrown brush, while also providing a highly stabilizing root system. The field of fluvial geomorphology is beyond the scope of this course, but it is important to understand the basic concepts that predict riparian health and give clues to activities that may be hindering recovery. Common understanding of terms is essential for communicating about riparian conditions. We will begin introducing some common terms. Ecologists classify water bodies as either lentic or lotic. Lentic, also known as lacustrine ecosystems, is a system characterized by still water, like lakes, ponds, and swamps. Lotic water bodies, also referred to as riverine ecosystems, is a system characterized by actively moving water. This course is focusing on lotic or moving water systems, but riparian areas are also valuable to lentic systems. Free-flowing streams will usually include a variety of features. Riffles are shallow, fast-moving areas where breaking water is visible on the surface. Runs are swift and can be shallow, but the surface is smooth and not breaking. Pools are deeper and slower moving than runs. The sequence of riffles, runs, and pools is an important factor in the aquatic habitat, but are also key energy dissipating features. Another important characterization of streams is their relative size within a drainage basin. Order classification range from first order, the smallest, and with no perennial tributaries, To the 12th order, the largest. The world's largest river, the Amazon, is a 12th order stream, and the Rio Grande would be an 8th order stream at its mouth where that enters the Gulf of Mexico. It can be useful to know the stream order and reach classification when examining a riparian area's plant community.